Thank you. Welcome to HashiConf EU. We're really excited to see all of you here. It's our first ever official conference in Europe. Seth and I and much of our company have tried to always maintain a strong presence and come speak at events in Europe, but we're really excited to actually have an official HashiCorp event here, surrounded by so many of our users and customers and partners. I think it's going to be a great couple days. Everyone should learn a lot about everything. And we also have more than a dozen HashiCorp employees here, so you could learn anything about HashiCorp you want. If you have a question about any product, we have all products represented here. Full-time committers and engineers from every product are here, so you could learn, and there shouldn't be a question we can't answer here today. All right, so I'd like to get started by first talking a little bit about the company, a little bit about HashiCorp, and the thing I want to talk in particular about HashiCorp is vision. I want to better explain what the HashiCorp vision is, because I think as users or potential users of the tools, it's important to understand what the vision of the company is behind the tool that you're adopting. There was something that somebody said 5 years ago that I heard that really resonated with me, which is the reason why vision is so important. Vision gives anybody the future post that you want to head towards, the thing that you're moving towards. And if you don't have a vision, if you only act on short-term decisions or what's popular now and what's popular just directly tomorrow, then any decision you could possibly make seems like the right decision, but puts you in a bunch of different directions and you end up going nowhere. When you have a vision that you're heading towards, you could visualize your decisions today and tomorrow. Are they pushing us towards what we want to achieve, or are we actually going backwards or going around in circles? So at HashiCorp, we pride ourselves on having what I believe is a very, very strong vision, something that we've always pushed towards. And in one succinct phrase, the way I would describe that vision, sorry, this is the wrong slide. I'm confused. I'm sorry. This shows the right slide, but this isn't showing the right slide. Okay. It's this slide. So the way I would describe, these are wrong. The way I would describe the HashiCorp vision in one phrase is that we provide infrastructure software for the future. We like to build infrastructure software to help you automate various parts of your data center, just like Zebia said. But we always like to think of the future and keep in mind what's coming next and build towards that. And I think that anybody using any of our tools could see how our tools solve problems today, but are built in a way to support things in the future. And the reason we do this is because, is because the state of software today is such that software is driving the economy. And what I mean by software is driving the economy is if you take a look, the best example I could give is if you take a look at the top 10 public companies in the US today, 5 of those 10 companies are very strongly software companies. I would argue that more than 5 are actually software companies, but 5 are unarguably software companies. And if you look 10 years ago, only 1 out of the 10 was a software company by any stretch. So in just 10 years, over half of the biggest companies have been replaced by software companies. And these aren't companies that are selling software necessarily. Some are and some aren't. But there's companies like Amazon up there, companies that are delivering physical goods to your door, but using their software and their edge with their software to do it better than anybody else. And if you look at the top 100, this example becomes even more dramatic. You start seeing things up there like car companies that are using software to deliver updates faster than ever. One of the examples I like to give is Jeep and Tesla. Last year, Jeep had a recall where it cost them tens of millions of dollars to recall cars only to replace software. It wasn't a hardware thing, but it cost them tens of millions of dollars. Tesla found 0 days in their software, but they were able to ship an over-the-air update, and it cost them, relative to Jeep, cost them nothing. So this is a huge difference and a huge differentiator that allows companies today to compete. And so to compete, every company, regardless of industry, has to look at how they could rapidly produce software in order to be competitive and gain an edge with their business. And so to do this, they need to do what we say, invest in infrastructure. And this is in an abstract sense. In the same way that governments invest in roads and that sort of infrastructure, companies need to invest in their own software infrastructure in order to more quickly develop software. And that's where we try to come in. So in the past, these are the properties of the infrastructure that companies have worked with, and it's just not good enough today. These are things like manual processes, insecure systems, or not thinking about security, constrained resources, and complex workflows. And I think that everybody could think of, whether it's within HashiCorp or just within the greater industry of other tooling, can think of ways that we've moved past this. Cutting-edge companies have moved past this into the future, which I would describe as automated processes as much as possible, secure systems, and really starting to think and care about security at a deep level in everything. Elastic resources, getting things on demand as you want them, and empowering workflows, giving developers and more people more power to make change more quickly. And this is what HashiCorp is building. So this is what I mean when HashiCorp provides infrastructure software for the future. To do that, we've built 9 tools. We've done a lot of things, but this helps explain why we have such a diverse set of tooling. Why do we create a tool like Vagrant, which is a developer-focused desktop software, and then create tools like Nomad, which is a distributed cluster manager that runs in your data center? The people that start adopting Nomad are usually very different than the people that start adopting Vagrant. And it's sometimes odd to think about a company that would make those two things and yet talk about them so much. But I hope that by understanding our vision and trying to see where we're trying to get to, it makes a lot more sense of why we have these tools and why we put them together. And across all our tools, while you could use them individually, as I'm sure a lot of you do, they've always tried to fit together in a cohesive way. And this isn't how they have to be used. People use them in all sorts of ways, but we always try to provide a clear line through our tooling. And we build all these things according to the Tao of HashiCorp. We have a very strong, principled approach to how we build tools. And so, like I started out by saying, we try to build software for the future. If you ask any of us, we may not tell you, but we think about solutions and what we're going to build 3 months in advance, but also 3 years in advance. We like to know what features we're going to ship in our current projects, but also what new tooling we're going to create years from now. And in doing so, we always keep an eye out on what other people are doing, how things are fitting together today. Are there other people that align with how we view our vision? And so earlier this year, there was an idea we had last year that we started working on earlier this year. And we started architecting it and planning it, and we're just about to start building it. And I want to talk a little bit about it today. It's called Vectra, and it's probably something that isn't what you expect. It's not software, actually. Vectra is a company. We've acquired Vectra. Vectra's joining HashiCorp and actually started working with HashiCorp 3 years ago. And we have incredible respect for this team. Vectra builds software in a way that aligns with how we would build software. When we looked at what they've built, including how it works, the code, why they built it, it could have come out of a HashiCorp playbook. It could have been exactly what we did. We were really, really impressed with the technology and the people. And what Vectra did was build a tool called Current. And Current is a distributed log aggregation and search system. And we took a look at it. Their solution's closed source, but we took a look at it. We looked at the architecture, and I honestly believe it's the world's best log management system. And so when we had the opportunity to bring this into HashiCorp and work with it, we jumped on it, and Current is now part of HashiCorp. Like I said, the team started working at HashiCorp months ago, and we're not open sourcing Current today. It's not available today, but they're working really hard to integrate it into our existing systems, and we're going to talk more about why HashiCorp acquired this company, why we wanted this technology, and why we planned on building something like it anyways a little bit later this year. So I'm going to leave it at that, and I'm proud to announce that they joined us, and I'm very happy that they joined us, and you'll find out more about how Vector and Current fit into the HashiCorp tooling a little bit later this year. So with that, I'm going to start talking about our tooling. And so we have a few tools to talk about today, a lot of major features that we're going to be shipping. And I'm going to start with Terraform. So Terraform, for those who don't know, is our tool for representing your infrastructure as code, building it automatically, and iterating on it in the future. You could represent entire data centers, including switches and load balancers, multiple data centers, all with code, and bring it up in one command. And in 1 year, Terraform has grown. It has three times more providers in 12 months, 3 times more resources. Resources are what we call things like servers and what it could support, what it could build, and 3 times the contributors. So this isn't just brute force hiring HashiCorp employees and growing the project. This is everything overall has been seeing massive growth in the past 12 months. And our focus, the mantra that the Terraform team has been going down over the past few months, has been trust and confidence. As this tool is being used more and more in production workloads and highly in environments where downtime simply can't happen, we really wanted to improve upon the trust and confidence of using a tool such as Terraform. So to do that, the first thing we looked at was state management. Terraform state is the way that Terraform stores how it views the world. So what are your current servers? How do they relate to each other? What are their properties? Terraform state is what has that information. It's used by Terraform to generate what's called a plan, to generate what Terraform's actually going to do. And it's really important that this state stays in sync across teams. And this is really where the pain started. So with state, if 2 different users have different versions of the state, you run into a lot of trouble. So how do we keep that better in sync? And with the state, how do you do things such as refactor resources, move them around, renaming resources? How do you work around buggy behavior? If Terraform did something wrong and you had to do it manually outside of Terraform, how do you reinform Terraform of this fix so Terraform doesn't reintroduce the buggy behavior? And above all, more than anything, anytime someone was manually modifying the state, it was a really frightening experience. Whether you were a beginner or advanced, it always felt extremely brittle and scary. And we wanted to address that. So the first thing that we worked on was a state management CLI. We wanted to make sure that anything you were doing manually, you're now doing through an official recommended way to do things. So the state management CLI for Terraform is a command line interface to view and manipulate Terraform state. It's different from the other Terraform commands in that the output is purposely Unix tool friendly. We expect you to script this stuff. We want you to be able to slice and dice it from the command line. It's different as well in that all Terraform commands generate a backup, but these commands generate backups with timestamps attached to it, so that after running a series of state management changes, you'll actually have a time step for each step taken. You could step back through the changes, and you could always get back to where you came from. It's very important. And the overall goal of this CLI is that you never have to manually modify a state file. So to look at some of these, going from basic to a little bit more complex, you're now able to list the things that Terraform sees in its current state. You're able to filter on those things. We're able to show more details about a specific thing. So in this case, we're digging deeply into a module to find all its properties that it has. You could rename resources, and you'll see that this is pretty Unixy. We use MV in the same way that it could move things, but it could also rename things. You don't just rename things, you could actually move things into other places. So in this case, we're moving an instance into a module. And you could also move things to completely other state files. So if you're refactoring a large infrastructure and you're actually breaking it down into multiple Terraform configurations and multiple Terraform runs, you can now move things from one Terraform state into a completely other, removing it from one and adding it to the other. So we're trying to give you these tools in order to do whatever you need to do with the state. And in doing so, we also unified on this syntax that we're using up here, which is what we call resource addressing. So resource addressing is what you use to reference reference attributes within your configuration. It's what you use to target operations on apply. It's what you use for all the state management, CLI. And we're working very hard to make sure that resource addressing is uniform across anything that ever needs to address a resource. And the syntax for it is really simple. And most of them are optional. So it's module, resource, type, and then index. And so some examples. Here's the resource. Here's the name for it. And here's a count. And here's what it looks like. And so an address for the first one, for example, would be AWS.web0. If you wanted to reference all of them, you could omit this specific index. And that's missing some slides, but that's that. The other thing that we wanted to do with state is make it clearer when state is modified. A lot of painful parts about state happened when Terraform updated the state without the user expecting it. And that caused state to be not in sync across different users. So now Terraform will only modify state on a refresh and apply. That's it. Plan will no longer modify state. And you could be confident that the only things that will modify state are those two operations, which I think are very obvious that they would modify it. We've also been working really hard on Terraform Enterprise to bring state management into there. We have a lot of Terraform Enterprise customers here today, so for those customers, this will seem familiar. So with states, we're able to list the state history in a similar way to commit history. You could see the history of the states. You could see diffs between versions of what happened to the state in a very normal red-green syntax. You could roll back state to a very specific version. If you wanted to go back 5, you could do the rollback. And you could also just dump the raw state if you actually just want to put it into a file or work with it with that state management CLI locally. And another important thing to mention is that state management CLI works completely the same whether you're modifying and manipulating local state or remote state. It's all the same. The next feature I want to talk about, which I think that Terraform users will be really happy to hear about, is lists and maps. So lists and maps are now a first-class variable type in Terraform, and they could be used with all variables, module inputs, and outputs. So for those who aren't Terraform users, this is what lists looked for before, or today, really. In Terraform before 0.7, here's what a list looked like. They didn't exist, so you had to hack around them. You would create something like a variable that used a comma as a way to separate items, and then to access a specific item, you would split it and then access a specific element. It's clunky, it doesn't feel right, and so now it looks like this. You could actually say a type's a list, you reference it as a list that feels very familiar, and you index it like a real list, because it is. And maps are very similar. Maps look like this, and you access them instead of a numeric index, you access them with a key. And you're able to pass these things into and out of modules as well. So now you could represent things like tags and so on directly through modules. The next thing I want to talk about is data sources. Data sources are a major new feature, and they're a new type of item in the configuration. They allow you to reference external data to be fetched by Terraform when it runs. And we used to use resources to simulate this, but it caused a lot of strangeness. So a lot of times people would run Terraform plan and notice that everything in the Terraform plan just said computed. At that point, the Terraform plan is less useful because it's not really telling you what it's going to do. And the main cause of this we found was a lot of data that we were fetching that we weren't modifying things, we were just fetching data. So we now represent this as a first-class thing in Terraform. It looks like this. Here's a real working example. So in this case, we're using a data resource, which is represented as data, to find an AMI. So this actually does a search for an AMI. In this case, we're trying to find the most recent AMI that has a name matching this wildcard. And after we find it, we use the interpolation to spin up an AWS instance with that AMI. And the really nice thing about this is when you run a Terraform plan, it fetches the data source as part of the plan so that you could see the AMI value in the plan is already computed. You could actually see what the value is going to be. If you simulated something like this without data sources in pre-0.7, that would all just say computed all the way through except for the instance type. And it's a lot harder to reason about. So you could use data sources for things like AMIs, disks, storage devices, pretty much anything. And just like anything else in Terraform, they're pluggable. So if your company has its own way of pulling data, you could write your own data sources and pull it and use it within your Terraform configurations. And the final thing I want to talk about with Terraform is something that has been asked for a really long time. It was probably one of the first 50 feature requests ever in Terraform. We've been working a really long time to figure out how to do it, and we're announcing the first part of it today, and that is import. So import allows you to bring existing resources that are created without Terraform under Terraform management. And this is a multi-phased plan to make import more fully featured. So what I'm announcing today is just the beginning of what import will look like a year or 2 years from now. So the first phase of import, and what I'm announcing today, is single resource state only. So what this means is that you could import one resource at a time. It'll fully generate the state it needs, but you'll have to write manually yourself the matching configuration. Phase N, which is what we're going to get towards and already have the plan for how to get there, is going to be a fully automatic supervised import and configuration generation. It's going to take a while to get there. We already have it planned out of how it's going to work through the releases and how we're going to do that. But we're going to ship it incrementally so each feature provides its own value. So today we're doing just phase 1 of this. And it looks like this. So here's the output and the command to import an AWS instance. It's really simple. You specify what you want, you specify its ID, and it brings it in. This works with more complicated things in the Terraform world as well. So in this case, we're importing an AWS security group, and that actually fans out to multiple resources. So in this case, it imports the security group, but also imports the security group rules as separate resources as a best practice within Terraform. And from the first example, like I said, it's state only. So the first example, if you ran a Terraform plan, it would mark it for destruction. Since it's not in the configuration, Terraform would want to destroy it. But if you make a matching configuration and then rerun the Terraform plan, there'll be no changes. So you'll have successfully imported existing resources into Terraform. So like I said, import allows you to bring existing resources. It has broad AWS support today. It's very easy to add support for new resources, and we'll be releasing it, expecting and hoping the community will add import support for effectively everything else. It really is really easy to do that. So Terraform, these are the major new things coming to Terraform. We have improved state management, native lists and maps, finally, data sources, and importing existing resources. And these are all going to be part of Terraform 0.7, and the RC is available today. The final release will come very shortly. So you could start playing with this right away today. The next thing I want to talk about, moving on to more projects, is Nomad. So Nomad is the tool we announced last year at HashiConf US. It's a cluster scheduler. It can schedule Docker containers. It could schedule binaries. It could schedule VMs as well. And last year, as part of the keynote, we announced a case study we did with DigitalOcean. And the case study we did last year was running Nomad on 3 servers with 400 clients and launching 1,000 containers. And we wanted to see how fast we could do that. We announced the results last year, but even at the time during the keynote, I alluded to the fact that we were planning something much bigger. And already at the time, we were working with Google in order to do this. We did the 1,000,000 container challenge, and we announced this a couple months ago. And what we did with this was we launched with 1,000 jobs and 1,000 tasks per job on 5,000 hosts in Google Cloud. We launched 1,000,000 containers and to see how fast we could do that. Like I said, with everything HashiCorp does, we try to make it work at the largest scale, and we really needed this to work. These were the results, and so we launched 1,000,000 Docker containers, and you could see here that the orange looks a little red. The orange is how long it took to schedule the job or the task, so that's how long it took to find where this container should run, and you could see that that line's pretty much linear. The gray is how long it took for the client to act that it had received the scheduling allocation, for the client to say, okay, I understand I need to launch a Docker container here, I'm going to start doing that now. And then the blue underneath is how long it took for the container to be running. And to measure this, we actually waited for output to come out of the container. So this doesn't mean that we talked to Docker and asked it to start it and we're done now. This means that we did that and the container is actually running. And so you could see that most of this is pretty linear, and we were able to start 1 million containers in just over 250 seconds. And that's really, really fast. When you break it down, we were actually able to schedule each container in just a handful of microseconds. And this continued, this speed didn't degrade over time as we increased the number of containers. It pretty much held linearly throughout. And when we announced this thing, one thing came to mind. The only negative feedback we really received was people saying, it doesn't matter because nobody runs 1 million containers. And when they said that, we really thought back to this quote that Bill Gates said, which is 640K ought to be enough for anybody. And the reality is, we have a customer today using Nomad that's deploying customer to 100,000 cores today. So we needed it to scale to that amount today, right now. Besides that, the architectures of tomorrow are going to require a scheduling load that is unlike anything that we currently have today. Think of things like Lambda architectures, where every request may be a scheduled event. If you think today, we're scheduling one thing for a web service, and every request is directly going through there. But a few 100,000 requests per second is not very much. And if you imagine that each request is a separate scheduled event, you're asking your scheduler to schedule hundreds of thousands of things per second. And so 1 million starts to become not that audacious. And besides Lambda-based architectures, there's also data workloads, things where you would launch a data job on something like Hadoop or Spark, and that has to suddenly schedule hundreds of thousands of tasks really quickly, out of nowhere. And then the last thing I like to say is talk about airplanes. So this is a video of Boeing testing the wing flex of their 787. And they designed it to work within a certain parameter and bend to a certain point. And they were able to test it to exceed 150% of what they designed it to be. And I looked this up, and I talked to a lot of people in the aviation industry. And the point to which this wing bends to has never, ever been recorded in history. Like, there's no point that an actual flight, a wing has ever reached this bend point. And so it's very similar in the fact that why design a wing that could bend that far if we fly millions of flights all the time, and a wing has never, ever bent that far? And the thing is, now that you know the wing bends that far, you know that in the worst storm imaginable, that's not going to be the failure point. That's not going to be the thing that causes the plane to have trouble. In the same way with Nomad, your steady state might be only a few thousand jobs, but when you receive the batch workload where you suddenly have to schedule hundreds of thousands instantly, as quickly as possible, you know in that scenario that Nomad's scheduling speed and ability to run those things is not going to be the failure point. That's not the thing that's going to cause you problems. And I think a lot of us here understand the fact that having less things to worry about is always beneficial. And so this is why we've done this. We believe it's important for architectures of the future, but we also believe it's important today for these bursty workloads. So we've been working on Nomad, and we've been making it better and better. And similar to Terraform, the thing we've been working on the hardest with Nomad is what I like to describe as developer and operator confidence. We want to improve the confidence when you run Nomad that it'll run the job that you tell it to run in a speed that you expect it to run in, and with a stability that you also would expect. And as part of that, we built a feature called Nomad Plan. One of the core tenets of HashiCorp software is declarative over imperative. We firmly believe in declarative as the approach for large scale. And what we've learned is with declarative systems, you need to have a plan. Terraform has a plan, and it's a big differentiator between it and other things. Today we're talking about Nomad Plan, which is a big differentiator between it and other schedulers. Because working with these customers that are deploying to scale, such as 100,000 cores, they reach a point where the fear in a declarative system is actually the unknown in what it's going to do. The benefit of an imperative system is you get to tell it exactly what to do. You feel in control. With a declarative system, it feels a little scarier because you're telling what you want to happen to a system, but you're not telling it how to get there, and you're you're not really sure if you agree with how it's going to get there, and you want some more confidence. Terraform Plan gives you this confidence. Other systems like Terraform struggled with this at scale too. A lot of people used non-Terraform solutions to bootstrap data centers, but didn't use them anymore to maintain them because it was so scary of what's going to happen. In the same way with schedulers, we actually started getting concerns with, it's great to get started, but at a certain point, there's a lot of fear and uncertainty when you tell Nomad to run a job, is that going to succeed? Is that going to cause downtime? Is that going to evict something that I don't want evicted? And so in doing that, we designed Nomad Plan to answer these questions for you. So Nomad Plan shows you the changes in your job specification, shows you the diff of what it picks up from your job, shows you how Nomad would allocate it at that point in time, explains if sufficient space is available, and if it's not available, why. And then you could use something called the plan index to also ensure that there's no race between you and somebody else deploying conflicting jobs. And here's what it looks like. And for Terraform people, this will look really familiar. So Nomad Plan, you run it against your job. Here's an example where we're running it against a brand new one. So the diff here is that everything is new. Everything has a green plus sign next to it. Everything's new. We run the dry run of the scheduler, and the dry run of a scheduler is that it actually goes through the scheduler and allocates it, but then just doesn't start it. So it runs through the full process. This isn't a separate side implementation. This is running through the actual scheduler. And it tells you, in this case, that everything's successfully allocated. And it's important to know that this doesn't reserve that space. This is a point-in-time allocation. If suddenly between here and when you run it, someone exhausts the space, it is possible for the actual run to not allocate successfully. But in practice, what we've seen is that workloads aren't usually that volatile. They're not changing that often. And so between the time you run plan and between the time you run, this is usually accurate. And then the last thing down here is the job modify index. So if you take this number and you pass it into Nomad run, it's sort of like a check and set. It won't run this job if the job was modified by somebody else in the meantime. Let's look at a different example. So here's an example where it's new again, but the allocation actually fails. So in this case, you see the diff, which hasn't changed, but the dry run in a warning color shows you that the allocations actually failed, or wasn't able to place everything. And then below that, it actually tells you why it wasn't able to place them. In this case, on one node, it ran out of available CPU. So this wouldn't be able to actually run right away when you schedule it. And here's an example of a change job. So in this case, you could see what changed. We changed the max file size megabytes from 15 to 5 for logs. And you could see that this forces in-place updates, which is nice to know that we don't need to destroy and create things. This could be done in place. And then in the dry run below, you could see that everything schedules properly. Here's a different example where we change the way something is started, which actually requires us to stop and start the job all over again. And so you can see this is a create destroy update. That means we're going to create the new jobs to destroy the old ones. But you could also see in the scheduler dry run below that you've configured it to do a rolling update, and we tell you that. So you could be confident that you could see the change, and you could also be confident that we're going to roll the update every 10 seconds, so it shouldn't cause downtime. And that's Nomad Plan. The next thing we did was live resource usage. So since we announced Nomad, this is a slide from when we announced Nomad, you've had to assign the resources to a task. You've had to tell it how much CPU, how much memory it needs to run. And this is not a thing that we're used to thinking about. We're used to running jobs on overly large machines that have more than enough resources. So we've never had to say at a decently detailed level how many megahertz in a computer we need, how much memory we need to actually run. And so figuring out these numbers was difficult. And the way we recommend doing it was over-allocating, using monitoring systems, and then toning it down to a more correct number over time. But today, this will now show you real live resource usage. So before, this command would exist, but the CPU and memory would just reflect whatever you wrote in your job specification. It wasn't really what was being used. But with the new version of Nomad, these numbers are accurate to what it's actually using at a point in time. And we'll color all the outputs so that you could quickly, in longer output, you could quickly find jobs, nodes that are oversubscribed or using too many resources that they weren't supposed to be using. In addition to just seeing simple CPU and memory usage, you're able to dump more detailed statistics pretty much across everything. So when looking at a specific node, for example, you can now see detailed memory, disk, and network statistics. And all of these numbers are real, actual, live resource values. And you could get all this out of an API, too. So you could use this for automated systems if you want to. And here's more examples of statistics you get. And so using these stats, you can much more easily pick the right numbers for your existing jobs, but also find misbehaving jobs and oversubscribed nodes and react accordingly. It gives operators a lot more tools built right into Nomad in order to operate it successfully. We improved the bootstrap and upgrade process for Nomad. These are small changes, but have a big effect on how easy it is to run Nomad. So servers now send the list of servers down to clients every time they heartbeat. This is important because as you add new servers, remove old ones, eventually over time, the servers that a client originally started with may no longer exist. They're actually all new. And now when you start up a new client, they'll use the right list. They won't lose the servers. They'll have all the new servers. So this lets you roll servers immutably without worrying about your clients. And we've introduced a console-based bootstrap. So if you're already running console in your environment, you don't need to run console to run Nomad. But if you do have it in your data center, then you could point Nomad just to console, and it'll bootstrap using that. So you no longer need to tell it where the Nomad server is, how to find it, figure out static IPs or any of that. You could launch anything anywhere in any order, and Nomad will coordinate with console in order to get the bootstrapping done on its own. And so this gives you a zero configuration start of your scheduler. So that's Nomad. We showed how we tested it at a really massive scale and our reasoning behind that and why we think it's important. It aligns with how we build tools for the future. We had talked about Nomad Plan and how important it is to have a plan in a declarative system. We talked about live resource usage and how you could use that in order to better understand your system. And then the easier bootstrap and upgrade process just to make it even easier to run Nomad. And this is all part of version 0.4. And just like Terraform, the RC for it is available today, right now. So we're going to talk about another tool now. And that tool is going to be Vault. There's a lot of Vault talks here over the next couple days. So with Vault, with Terraform and with Nomad, we focused on improving confidence and trust. With Vault, what we're really moving towards is what we describe as closing the gap. And the gap in this case is the insecure gaps. So if you look at a security system, it secures various things, but it leaves a lot of things untouched. So with Vault, we're taking a look at, okay, secrets and storing data is good. Certificates, that's now secure. What isn't secure anymore? And finding those gaps and closing them down. Before I talk about how I did that, I do want to mention that 0.5 has been fully audited. So 0.3 was also audited, but 0.5 is a more recent release that was fully audited and passed with flying colors. And to talk about going back to closing the gap, the first feature we built is something we call response wrapping. So one of the issues we ran into with Vault is the sort of last mile problem with Vault. If you request a secret out of process and you're now handing it into a process, let's say an environmental variable or into a file, it's now decrypted or unencrypted and no longer secret for that brief duration. And that's a gap that we wanted to get rid of. And there's always been a solution where you could deeply integrate Vault into your applications, but that has complications in terms of how do you authenticate, how do you maintain your authentication, how do you renew things. There are some struggles with that. So we wanted to close the gap by providing a middle ground, a better middle ground. And we call that response wrapping. So what response wrapping does is it allows another system, which already is fully authenticated and talking to Vault, to request a secret. And when it requests that secret, it asks Vault to wrap it. And what that means is Vault generates a new identity, a one-time authentication token, in order for you to unwrap that secret. So what then happens is the wrapped value could be sent into the process with its token, and then with minimal vault integration, that application could then request the secret and unencrypt it. And so it's only insecure in a sense for a very short period of time, but it's no longer just plain text. So as an example of what this looks like, if you write a secret just in the normal style, you could read it and provide a wrap. And in this case, we're saying we want to wrap it and keep it valid for the wrap valid for 60 seconds. After 60 seconds, you can no longer unwrap that value. So you can see the result is not the actual value of the secret anymore. The result is a token and how long you have to use that token. So instead of passing the raw configuration to the application or the environmental variable to the application, you now pass that token to the application, and with a very lightweight integration, that application can unwrap the value and get the actual unencrypted value out of it. The next thing we did is the AWS EC2 auth backend. And this is closing the gap of how do you get your first secret onto your server. When you launch a server in AWS, how do you get the authentication token to authenticate to Vault onto that server? And so the AWS EC2 auth backend lets EC2 instances automatically authenticate with Vault without having to pass in a token. And the way we do this is treating Amazon itself as a trusted third party, using that to verify the instance, read various properties of the instance, and use that to assign identity to the machine. This dramatically simplifies tasks such as autoscaling, using things like Terraform with this. And the way it works is pretty simple. You launch an EC2 instance. As part of launching the EC2 instance, AWS assigns an identity that it signs to the instance. The instance then asks Vault to authenticate it, and then Vault takes a look with Amazon, verifies that identity, that they actually wrote it, and also checks a bunch of properties such as tags and subnets and other things in order to figure out what permissions this EC2 instance should have, and then just gives it the token. And so because of this, you could just launch the EC2 instance. Just shortly after boot, you're fully authenticated, and you get rid of the bootstrapping problem. It's fully automated. So we've done this with AWS, and we're working with other cloud providers to bring it there as well. And all of these features are part of Vault 0.6, which is fully released today. And so that wraps up all the product updates. I think we had some really exciting updates across a bunch of products today. Plan across Terraform and Nomad, better security across Vault, and really showing maturity in every single project. And with that, thank you, and have a good time at HashiConf. I'll go back to Seth.